Okay, if we could all kindly make our way over to the seating area here. I just would like to introduce myself. So my name is Steve Goldsmith. I'm assistant professor in the Department of Geography and the Environment and the current president of the Sigma Xi Honor Society. And I just want to say it's been a joy walking around here today, seeing so many people actively sharing their research. And this year we had a record of 63 participants, both undergraduate and graduate students. So first and foremost, I think it would be nice if we give all our student presenters a round of applause. And also, I would like to acknowledge the effort of the judges as well, and simply without you, we cannot make this event work. So again, an additional thank you real quick. So in a few moments, we'll have our keynote address by Dr. Dan Nocera, and those of you that were here on Wednesday saw what I would call a captivating talk, and we're pretty excited to get basically the sequel with regards to the artificial leaf here today. That will be, the talk is going to be promptly followed by our awards ceremony, so if there are any judges in the room that still have one of these, please hand them to me on the way out, and we'll be tallying them up in the interim. And finally, I just would like to invite Father Cale Ellis, the Vice President of Academic Affairs, to come forward and just say a few words. Thanks.
I will be brief because you're in for a real treat with Dr. Nocera's talk. Those of you here Wednesday, you know, he has a right sense of humor as well as a deep knowledge of his topic, and we learned a lot. At least I learned a lot, and I'm sure you will as well. Sigma Xi. Those of you who know, we're familiar that we have this award that we have been giving annually for the last almost 20 years. It's called the Mendel Medal, and the recipients are always very obviously prominent. They were scientists, but also scientists who are see no conflict between science and religion, and almost invariably, all the recipients have been listed on their resume members of Sigma Xi. The other commission that they're a part of is also the Pontifical Academy for Sciences. I don't know if that's not necessarily a correlation there, but regardless of their faith tradition, they would always seem to be in that. So the two areas here. And of course, there is a lecture that's sponsored by Sigma Xi with the College of Arts and Sciences, you know, by the recipient. But what I would like to do is, certainly I'd like to congratulate the undergraduate and graduate students who are presenting these posters and who are up for awards this afternoon. And I'd like also to say a few words about research and its importance here at Villanova. And this is certainly a great event, and we celebrate your accomplishments, and also your accomplishments which kind of fit in very, very closely with the educational ideals of the university. Not long ago, I think it was rare, especially for undergraduates, to become, you know, really involved in scientific research. But today, this experience is, you know, fairly typical and something that we certainly want to continue to encourage. And we do that because the research gives students a taste of what a career in science or in engineering would be like, and it is also an edge in applying for graduate school and jobs. But the edge, as we are told, is not quite what it used to be, because many graduate schools and employers in particular have come to expect it. And so engaging in research isn't only helpful for graduate-bound students, graduate school-bound students, but a substantive research experience can help recent science grads and engineering grads land interviews and even jobs in the industry and compensate for maybe years of experience, quote unquote, listed in job advertisements. And so research is also a significant confidence booster. The students are mentally stretched, as we know, wrestling with surprising results for unanswered questions or pertinence, to previous studies, and the greater the sense of accomplishment upon completion of the project, the greater the satisfaction that you have, and you can go forward with that. But faculty who mentor undergraduate students in their research are especially to be commended. For although some faculty publish, particularly with undergraduate students, most really engage in mentoring primarily out of a love of teaching and a commitment to the development of their students. And they realize that independent research offers students a taste of the culture of research and of the life of a scientist. And so they engage in it, as it is a risk-free way for students to investigate whether a research career or a particular field is good for them. And so that establishment of a relationship with a faculty mentor, is certainly a big advantage for students, who are engaged in research. And it is shown as well, not only to be a supportive and a friend of the students, but also it increases retention and even graduation rates, we are told. And so the students benefit from the wisdom and from the knowledge and from the experience of their faculty mentors, and this is something we want to promote as well. And so, if science is truly your vocation, sometimes we have to be prepared for failure as well, or criticism of our work. Things don't always work out, but regardless of any negative results, when the moment of discovery comes, it will be truly exhilarating, and so you are to be congratulated in doing that. When I was talking about, I mentioned failure, I don't mean to be negative, but I was thinking of St. Augustine, who, over about 1,500 years ago, wrote this monumental book called The Trinity. And he somehow anticipated he was going to be criticized by people who read this book. And so he actually wrote, toward the end of his book, this comment to the reader. He addressed it to the reader. And I think that anyone who is engaged in research could probably meditate upon this and maybe follow his example. And it goes something like this. It says, "Let the reader, where we are equally confident, stride on with me. Where we are equally puzzled, pause to investigate with me. Where he finds himself in error, come to my side. And where he finds me erring, call me to his side, so we may keep to the path in love as we fare on toward him whose face is ever to be sought." So I think that openness, that sense of discovery, but also to know that we are not always going to meet with immediate success, I think it should be a consolation for us. But nevertheless, I think that today, we see your achievements, and we want to congratulate you and enjoy this particular moment. So thank you very much.
Thank you, Father Ellis, for that introduction. It's now my pleasure to introduce our speaker for the afternoon, Dr. Daniel Nocera, who is the Patterson-Rockwood Professor of Energy at Harvard University. He's widely recognized in the world as a leading researcher in renewable energy at the molecular level. His group pioneered studies of the basic mechanisms of energy conversion in biology and chemistry, with primary focus in recent years on the generation of solar fuels. He's recently accomplished a solar fuels process that captures many of the elements of photosynthesis, and he has now translated this science to produce the artificial leaf, which was named by Time magazine as Innovation of the Year in 2011. This discovery sets the stage for a storage mechanism for the large-scale distributed deployment of solar energy. Professor Nocera has received numerous awards, including the Eni Prize, the Berkhausen Prize, the Elizabeth Wood Award, and the United Nations Science and Technology Award. He's also recipient of the American Chemical Society Award in Inorganic Chemistry. He's a member of the American Academy of Arts and Sciences and the National Academy of Sciences. He was also named one of the 100 most influential people in the world by Time magazine and was 11th on the New Statesman's list of the same topic. Dr. Nocera has supervised 120 graduate and postdoctoral students, has published over 350 papers, given over 725 invited talks, and 80 named lectureships. Quite a busy person. In 2008, he founded Sun Catalytics, a company committed to development of safe and reliable renewable energy and to bringing personalized energy to the non-legacy world. And today, he will be speaking about his invention of the artificial leaf. So let's please welcome to the stage Professor Nocera.
So thank you, Amanda. Also, Jared, who had to take care of me for the last 3 days and shuttle me around. The Department of Chemistry for hosting me. Father Peter, who has gotten to know me more than he wishes right now, including me crashing the faculty reception and then again absconding with him, and Father Ellis for coming and saying something very important to the students. You really learn when you experiment and explore, and that's what I think today is about. And it's really the best way to learn anything, is when there's no structure or there's no book to read to get the answer, and you have to find the answer. That accelerates learning. And so that's why at Villanova, to have research so integrated with its teaching mission, it's a hand-in-glove fit. It just doesn't work if it's just teaching. And so it's wonderful to see. So today what I'll do is tell you about the artificial leaf. I gave a general talk on Wednesday, and I don't want to go over that too much. I'll just give you the highlights because there's maybe some people here who didn't see Wednesday. So I'll just, in the first few slides, try to orient people. But the whole idea is, and you can see this in the back, that's how you guys live, the grid, and there are wires on it. You can see I've already destroyed it in my mind. In practice now, I'm out to do the same thing with the artificial leaf. And this kind of tells you what it's about if you could give energy to the individual, so distributed energy, right? And today I'll talk about that. If you don't like the artificial leaf, which you might not, and there were lots of good questions from the students on Wednesday saying, finding all the weaknesses right away. Like, how do you use hydrogen? And that's a good question. And how are you going to move that and technology adoption? The one thing I really like about it is this idea that all this discovery made an energy system that's just really simple. And you don't need really complicated machines and equations and engineering to make it work. And so that's what you should look for today. And Wednesday was a general talk, so today I'm going to put some of the science behind how we did this. And so first let me just orient you. In a few of these slides people are going to recognize. But when you talk about energy, it depends on people, money, depending on how wealthy a country is, they use more energy, and then conservation. And so when you multiply the number of people and wealth per capita and energy per GDP, which is called energy intensity, you find out what the energy number is. And this is a summary of something I went through in a lot of detail on Wednesday. You currently use this much energy, that's power, because I know there are some engineers here, and they know the difference between energy, joules, and power, joules per second. So the way you can think about this, and I'm going to be sloppy. I'm going to use energy and power interchangeably. But what this says is you burn a 16 trillion watt light bulb, and then you need to give energy to keep the light bulb on. That's the way you can think about it. So the Earth burns a 16 trillion watt light bulb. And then I went through on Wednesday, and now you can take it, my word, that you're going to need to double it in the next 40 years. And then we went through some of this stuff, and I summarized it here in words, what I showed in numbers a few days ago. But if you took all the land, you only get 6 terawatts, and you have to build a nuclear power plant every 1.5 days forever to get 8 terawatts. And for the people who aren't there, if you want to ask a question at the end, I can back all this up. This is getting all the energy out of the earth. That's where it's drillable, because remember, in the middle of the earth, it's really hot. So if you're willing to drill to the middle of the earth, you'll be in good shape. That's okay. Wind. And so I made a case that there's a lot of solar. This is numbers. Again, you can see how many terawatts worth of energy is hitting the face of the planet. But I mentioned a little line on Wednesday that in 1 hour, all the energy the Earth uses in a year strikes the surface of the Earth and the sun in 1 hour. Right? So we're just not using it. And part of it, it's too expensive. But the other part is coal is too cheap, right? Because you guys can get coal very cheaply. So it's really not so much that the sun is too expensive or solar is too expensive, energy is too cheap. Something I didn't say on Wednesday, but I'll say it here. Solar energy is too expensive for rich people, but it's not too expensive for poor people. Right? And the reason I say that is you guys use 30 kilowatt hours at home of energy. So if I told you I'm going to give you 100 watts, you use 30 kilowatt hours a day. If I gave you 100 watts per hour, you're going to say, I'll take your 100 watts, but it better be really cheap, like next to nothing, because I don't really need it. Right? If somebody doesn't have energy and I tell them I'm going to give them 100 watts, that becomes a much more valuable commodity for them. So it tells you that energy in America is just too cheap. And we went through that. It's because you've invested heavily in it. So this was sort of the layout. And the layout was, why do you need so much energy? And it's because there's 3 billion people who will be born in the next 40 years. And there's 3 billion poor people. And if they're poor, they're not using a lot of energy. And so as these 6 billion people come on board in the next 40 years, and to give you a little number, in India, in the next 15 years, 350 million people will come from destitute poverty to the rising middle class. And that's the population of America in the next 15 years. So when you start having things like that happen, there's going to be a big energy need. And that's what's driving the doubling of the energy. And I showed some graphs saying that you need to have very simple systems if you want to bring energy to the poor. Because as soon as things become complicated, they start getting expensive. They start weighing more, and weight is energy. And that led me to say on Wednesday, this is my grand aspiration. I'm 55 years old. I wanted to be the McDonald's hamburger of energy. So that's my aspiration, right? And so build an energy system like a hamburger. And that's because if I could, then it's simple, it's lightweight, and it's highly manufacturable. So today I'll show you that scientifically. The place we went for inspiration in life was photosynthesis, because in photosynthesis, when light hits the plant, it rearranges the bonds of water to make oxygen and hydrogen. Then the hydrogen gets fixed with carbon dioxide and it makes a sugar. And it turns out that all the energy storage is in the rearranged bonds of water. Hydrogen plus CO2 is thermoneutral, no more energy storage. So in the plant, this front part where it splits water to make oxygen and hydrogen, that's why you're giving the plant water, that's kind of a fuel. The fuel is sunlight plus water. It makes hydrogen. Hydrogen's very energy intensive. The plant didn't know how to get its hands around hydrogen. It's a gas. So what it did, it fixes it with CO2 and makes sugar. But there's no energy storage here. That's called the Calvin cycle. Melvin Calvin won the Nobel Prize for that. But that's just the plant's way of storing hydrogen. All the energy storage is up front in solar energy water splitting. It's called water splitting. So that's the brief summary of Wednesday's talk, and now I'm going to show you all new stuff. All right, so now everybody has to listen. Okay, so I'm going to now look at photosynthesis, and I'm going to treat it as a systems engineering problem. And the reason I'm saying that is, if you're a biochemist or biologist, every one of these letters, like P700, I have PS1 up here, the cytochrome B6F complex. Every one of those is a big biological machine. And there's 50 to 100 groups around the world working on each one of these. This one's a famous one. That's called the ATP ACE, right? That one won the Nobel Prize too. John Walker from England. So you have to like a science named Johnny Walker. And then he won the Nobel Prize to boot. So John got the Nobel Prize for that. Melvin Calvin got the Nobel Prize for up here. I didn't show it to you. Rudy Marcus, my old code director, got the Nobel Prize for explaining how the electrons separate and move in the plant. And then the Germans, Diesenhofer, they got the Nobel Prize for solving this structure right there. And then Peter Mitchell got the Nobel Prize for the chemiosmotic principle, which was to say that biological energy is stored in the movement of electrons, which couples the proton transport. And he did it for this thing. So there's 5 Nobel Prizes on this slide, and that's just to tell you, don't take these things lightly. Okay, now I will take them lightly. So ignore all of that, and I'm going to now treat it like a systems engineering problem. So here's what a systems engineer would do. The light comes into the plant. The plant doesn't know how to get its hands around light. So what it does, and I'm not showing the light harvesting complexes up here. They're a huge grouping of proteins that do light absorption. They're like light antennas. And then they funnel the light. You can think of it literally as a funnel. It takes a big wavelength of light, the solar spectrum, and starts narrowing it. And it narrows it, and when it hits these 2 yellow ovals, that's called the special pair. I didn't even show it. The special pair is up here, 2 porphyrins. The light comes in there and it causes an electron to move one way. The electron heads out this way, jumping, and some of these arrows are showing you this. It jumps along these cofactors and it basically heads this way. If you make a negative charge, you have to leave a positive charge behind. The positive charge goes in the other direction. It doesn't have to go as far to the oxygen evolving complex, right? So what's that telling you let's now think of, this is biology. Let's be electrical engineers. Light in, and then I'm going to move a negative and positive charge. When you move charge, that's current, right? So what the plant does is it doesn't do anything different than what you do in the wall. You have solar light that gets translated into a high energy current. But the current is special, no wires. That's the big difference. So it's moving the current through this membrane. The electron comes this way to what's called photosystem 1, and the positive charge comes to what's called the oxygen evolving complex. The plant then does this 4 times. So it uses the sun to charge up this current by 1 unit of charge, a 2nd unit of charge, a 3rd unit of charge, God bless you, and then a 4th unit of charge, okay? And then once you get to 4 units of charge, the 4 holes, or the 4 positive charges, go into this cofactor, and I'm going to show you what that looks like. It's called the oxygen evolving complex. And that cofactor splits water to oxygen. And if you remember freshman chemistry, water splitting is a 4-electron, 4-hole process. So then you make O2. When you take the four electrons out of 2 molecules of water, you leave 4 protons. The 4 electrons that you then use to reduce hydrogen, remember the electrons were coming this way, they're stored over here in photosystem 1, which is in an iron reductase. When that gets charged up by 4 electrons, it takes in 4 protons and it makes 2 equivalents of hydrogen. But nature doesn't make a gas, it stores it as NADPH. That's nature's way of hydrogen. Then the hydrogen gets fixed with CO2 up here, which I told you is no more energy storage, all right? So now let's think about it from an engineering point of view. Light in, wireless current, do it 4 times, and then store the charge in 2 catalysts at the end of the charge separating network to then split water to make oxygen and hydrogen. So that's how it looks from a systems engineering point of view. The difficult step in this whole process, and this was called the Holy Grail of chemistry even up to 10, 15 years ago, is this water splitting reaction. That's the thing that was difficult to do under the conditions of photosynthesis. I do want to say it isn't difficult to do technologically. Since 1860, people figured out you could do electrolysis, water electrolysis. But they did it in a heavily engineered environment. It's expensive. This plant just grows outside. It does this very tough reaction using sunlight under simple conditions. And yesterday, in a very technical lecture, I talked the reasons why. One of them is quantum mechanics and physics. Electrons are delocalized. They spread out. They're like a wave. A proton is classical. It's like a ball, and its wave function can't spread out. And so it's a real problem at the most fundamental physics level, and it's called the two-body problem or incommensurate length scale. How does a quantum mechanical thing spreading out coupled to something that doesn't spread out, the proton, which is classical? And that's called proton-coupled electron transfer. And you got to do it with 4 electrons and 4 protons to boot. That makes it super hard. When my ex-co-director got the Nobel Prize, he only did the electron part. He never worried about the proton, because in physics, in case you've ever remembered the Hamiltonian or you take your physics class, notice they'll always solve it, but only for 1 electron. Then when it gets to 2 electrons, they say, they go like that, and then they, okay. So you can only solve the Hamiltonian explicitly for 1 electron. And this is 4 electrons, and there's 4 protons. And that's called in physics the multi-body problem. And then you got to break all these bonds. So that's what makes it tough. But I just told you we can go on Google and buy an electrolyzer, and you have 2 options. These electrolyzers use catalysts, like the oxygen evolving complex, but they're super expensive stuff. It's ruthenium and iridium and platinum oxide. If I want to give energy to 6 billion people, I can't use ruthenium, iridium, and platinum oxide. A lot of the students out there, this is going to come to play in your life a lot in the future. It's called critical materials. And what critical materials are, the Department of Energy just made a big announcement. We need to replace everything in America that we use with elements that we have control of. We don't have control of iridium, ruthenium, that we get those from overseas. And so there's a big push by the Department of Energy saying, how do we do what we do today using non-critical materials, materials that we have access to? So that is one issue. That's why I'm calling these critical oxides. You also have to use really expensive membranes. But if you use all these super expensive stuff and critical materials, you can do it out of you can do it out of water. It's not a glass, it's a highly engineered system. Alternatively, you can use simple oxides, non-critical oxides, like nickel oxide. That's simple, everybody has nickel. But nickel oxides decompose, they corrode. And so what happens is the engineers, being good engineers can take really not so great science discoveries and make it look super. I learned that at MIT. Those guys and gals can do anything, from what I can tell. So you can take kind of a really awful catalyst, but you can make it work once you find an engineer. But they work in concentrated base. If you start trying to do things in concentrated base, you have to have a heavily engineered system. So it gets expensive for a different reason. It's not because of expensive materials, it's because of expensive engineering. So we sat down and said, if we're going to be like a plant, we got to use simple stuff and simple engineering. And that hadn't been done before. And we thought if you could do that, you could operate out of a glass of water. But like I told you, if I'm going to use simple things, they'll corrode. And the corrosion is when you split water, you make protons. And protons are an acid. A metal oxide is a base. And if you remember freshman chemistry again, base plus acid makes neutral compound. So here we have base plus acid makes a neutral compound. The compound dissolves and you make water, and that's called corrosion. So we knew we had to make the first catalyst that didn't corrode. All right, that was the first thing. And there was another voice speaking to us, again, which we always listen to, and that was nature. So this guy, I told you there's 5 Nobel Prizes. I'm going to now predict the 6th Nobel Prize, and it's going to go to him. That's Jim Barber from Imperial College in London. And in 2006, he got the crystal structure of the photosynthetic membrane. The whole thing, you know, light coming in, the whole wireless current, pumping the protons, everything I showed you in the cartoon diagram, he crystallized it and then got the crystal structure. For the experts out there, it was a fuzzy crystal structure. It was a fuzzy, it's like I always say, the Kodak moment, all right? So it was a fuzzy picture. It was at 3 angstrom resolution. Last year, the Japanese group got it at 1.9 angstrom resolution. At 1.9 angstrom resolution, you can see everything crystal clear, including, you know that membrane I showed you? 2,200 waters in the membrane they were able to resolve. But the picture didn't change from Jim's original hypothesis, and here it is. Once he got that crystal structure, we could go inside and say, what does the oxygen evolving complex look like? And you know, I go to Gordon research conferences or science conferences, and we always talk about complexity. You know, scientists love complexity. Chaos, right? This is what these physicists tell. Complex. This thing is about as simple can be. All right, this is the Forrest Gump of cofactors in biology. It's 4 manganeses, 1 calcium, and 4 oxygens. It's Mn4O4 calcium. And it's in a dice cube. Look at the cube. It's a cube of manganeses and oxygens. There's a calcium. And that manganese there is called the dangler, named by a man named Dave Britt, who came from Texas. He's at UC Davis now, and he proposed in an EPR experiment in 1997, there's this manganese, I can't figure out what it is. It must be dangling. But he didn't even know what it looked like at the time. So there's the dangler and 3 manganeses and a calcium in a cube. And for me, Mn4O4 calcium, that's a piece of rock. That's what rocks are made out of, metal oxides, okay? And so you have a little piece of rock in a very special way, organized, and then you see these yellow things, these hands, and there's 1 green one, but those yellow hands are amino acids, and they're ligands from this transmembrane protein. So that yellow thing that's inserted, it goes across the membrane, it's a massive protein, and at the bottom of that protein are these arms, and that's where that cluster sits, and it self-assembles in there. And so now I'm going to tell you something about a plant that you probably have never known. It's making oxygen. And over here, it's making hydrogen and then sugars. The oxygen is toxic to the plant. So the oxygen starts eating the arms and starts decomposing the amino acids. So every 30 minutes, every chloroplast, every higher order plant that you see, it removes the D1 protein. As soon as it takes the D1 protein out, this cluster falls apart. When the cluster falls apart, it can't make any more oxygen. And then it takes sulfate, SO4 2-, which is a mineral. It changes sulfate to cysteine in a short biosynthetic pathway. And then from that 1 cysteine, it rebuilds this entire D1 protein, then reinserts it into the plant. So now it's all new again. And then the manganese re-self-assembles and the plant keeps working. So every 30 minutes, a plant is taking every D1 protein out and rebuilding it. So what the plant did, which we had trouble getting our heads around, it didn't, even though that's a rock, it didn't try to make it stable forever because it would have had to make it Teflonized. It would have had to put something that doesn't get corroded. The plant said, forget it, what I'll do is repair myself every 30 minutes. All right? So we wanted to do anti-corrosion or repair, and then photosynthesis was telling us to do repair. What do chemists do? Chemists don't listen to nature. We always say, oh, we're going to make a compound and it's going to be really stable. That's what everybody always asks, how stable is it? So you try to make something that doesn't fall apart. So we said we aren't going to do that. We're going to try to make a self-repairing catalyst, and that will allow us to work in water. Yesterday, I gave you the science behind these 4 points. So from 20 years of study, it took a long time to figure all this out. We figured out we needed to use cobalt. To make the OO bond, I told you there were 4 charged up units. You have to do 4 charges to make the OO bond. It's at the 3rd charge. You have to be very, very attendant to coupling it to a proton, that quantum mechanical thing of coupling the electron to the proton. It's after doing it 1 time, a 2nd time, at a 3rd time. You have to spend a lot of attention, because then you got to do proton coupled electron transfer, and that allows the 2 oxygen bonds to come together. I talked about that yesterday, and I put, I think, everybody to sleep. It was brutal. So just take it from me. That also came from our studies. And then don't try to prepare a stable compound. All right? Try to fix an unstable one. So that led Matt Cannon in my group to take cobalt, put it in a glass of water, add phosphate, HPO4 2-. We needed the phosphate to do this proton-coupled electron transfer. And then what he saw, cobalt is cobalt-2. So it's the ionization state of cobalt. And then he did an electrochemistry experiment. He started making an electrode more positive, so he's increasing the potential. And then at this potential, at 1 volt, you would take cobalt 2+ to 3+. So the cobalt that's in solution, we pulled 1 electron out of the cobalt that's floating around in there. And when we did, in the presence of phosphate, when we looked on the surface of the electrode, and the electrode could be powered by electricity out of the wall, or we could have hooked it up to a solar panel, doesn't matter, or a battery. So when the battery had 1.2 volts, we would take cobalt 2+ to 3+, and then we made this thin film we would see form on the electrode. And as that film formed, look at what we saw, all that oxygen. And then we proved to ourselves that every time we took, for every electron, every 4 electrons, we made 1 molecule of oxygen. It was 100%. The protons, I'm not showing you the whole experiment. Over here is another picture. The protons are being left behind. They have to run over to the other side, like in photosystem 1, and there's electrons waiting for them to make hydrogen. In that first picture, we did this 4 years ago when we discovered this, we were using platinum, and that's a critical material. And I told you we got to get rid of it, so you still have to hold my feet to the hot fire. But the tough reaction, water splitting to make O2, we did it by just, look at what we did, just dumped cobalt and phosphate in solution and charged it up, right? But like I showed you, that had that background that told us to do that. Okay, so now we have the compound. What is this thing? And oh, by the way, since we've done this now, this has become a cottage industry. Everybody's using this catalyst, right? So you can do it the way we did it. There are people like physicists and electrical engineers now who are using pulsed laser deposition and atomic layer deposition. So from the gas phase, you can lay it down on things like silicon. And you can take semiconductors and you can shine light on the semiconductor. Remember what happens in a semiconductor. When you shine light, you make an electron-hole pair. That's called an exciton. And the positive charge from shining the light on the semiconductor takes cobalt 2+ to 3+, and then this forms. You can't see it very well, but on those rods of zinc oxide are little dimples of the cobalt catalyst. So there's a lot of ways to make it. Now the question becomes, who cares? I told you in 1860, people did electrolysis. You might remember when you were in high school, your teacher may have put 2 electrodes in water and put a battery on them, and you saw oxygen and hydrogen coming out. So why were we going gaga over this when people in high school do it? And the reason is, what your teacher did so that you could see lots of bubbles, first, she or he's using platinum to do it. And then the second thing, so you guys could see bubbles, they started turning the potential up. It takes 1.2 volts to split water. But platinum isn't good at splitting water, so you have to go an over potential, past the thermodynamic limit of 1.2 volts, or you have to put a lot of extra energy into the system. And what you're doing, so what did the teacher do? Just kept turning up the potential until you guys saw lots of bubbles. When the teacher turns up the potential is a hole. It's the positive part of the current. As I turn up the potential, you can see this, I'm going to raise this well, and this is the reactant well. So this is reactants, water plus the electrode, and then this is O2 and the 4 protons. So when the teacher turns up the potential, what she's doing is, and he's doing, they're energizing the electrode, and as they energize it, remember the reaction rate depends on how high a hill it has to go over. So as I energize the electrode, the hill is tinier, so the reaction goes faster and you see more oxygen. And what we showed at any given over potential, so this is 0.3 volts past the thermodynamic limit of 1.2 volts. So we're at 1.5 volts. At any given over potential, the blue, which is this cobalt catalyst, is 3 orders of magnitude better than platinum. So not only is it replacing platinum with an earth-abundant metal, it has one extra thing going for it. It's 1,000 times better at doing water oxidation. And then you can ask, what is it? So what we did is we built an electrochemical cell, and then this is the end of a 2-mile long linear accelerator. That's the Stanford Linear Accelerator. So we got time on the Stanford Linear Accelerator. It's a DOE instrument. And then we charged up the linear accelerator. And from those high energy electrons, you can get X-rays out of them. And then we could shine the X-rays into the electrochemical cell as it's making O2. And then, using a thing called XAFs, it's a scattering technique, by watching the X-rays scatter, because that's what this big detector is, we could figure out what the structure of the material was. And guess what it is? It's that thing right there. So that thin layer of material that's on the electrode is just an insoluble molecule. And the insoluble molecule has 7 cobalts, okay? And then it's in a circle, a disk, and then the disk is capped off by the phosphate. Remember we had phosphate in there? And so you have what's called a cluster. That's what inorganic chemists call clusters, more than one atom. So we have a 7-atom cobalt cluster. The other thing is, look at a given cobalt. It has 6 ligands on it. So there's 1 oxygen, 2, 3, 4, 5, 6, and it's octahedral. That cluster made us really happy. And by the way, that's serendipity. All right, so I got to tell you what was planned. What was planned was everything I told you up until this point. Then, when we saw all the oxygen, we just thought it was some random polymer. We never could have believed that we would have made this simple, beautiful molecule. Why is it simple and beautiful? That's the cluster I showed you before, the oxygen evolving complex from Jim Barber's crystal structure of the photosynthetic membrane. If I double it, do a head-to-tail dimerization, and change manganese for cobalt, you get that, and you rotate it 45 degrees, you get that. So this thing ends up being the dimer of the oxygen evolving complex found in nature. That's total luck. There's no way I ever thought I would have made the cube with the dangler dimerized. All right? So every so often you get lucky in science. So that was luck. Then we want to figure out what it is. And so remember, we start off with cobalt 2, If I go to, I'm going to now use my fingers, cobalt 3, I got 1 electron out. Cobalt 4, I got 2 electrons out of the cobalt. And so when we did that, we could find when we add, before water oxidation, at a potential where you can't make oxygen, this cluster we could put into an EPR instrument. In EPR, you can get the magnetism and figure out what the magnetic signature is of an ion. So at 1 volt, we're below 1.25 volts, it's all cobalt 2. Then when we were seeing the oxygen bubble out, we would put it into an EPR machine. We found out we were cobalt 4. This black line, 1.34 volts, we're past 1.2 volts. That's where we saw cobalt 4. So now I have a cobalt 2, 3, 4. I have a cobalt 2. So here I'm going to energize my catalyst. So in the oxygen evolving complex, I said you pump it up with photons, 1, 2, 3, 4. I take cobalt 2 to 3, 1, cobalt 3 to 4, 2. That must mean I need another cobalt because I need 4 holes to do water oxidation. And so we knew this was going between a cobalt 2, 3, 4 couple. Now I'm going to be a geeky inorganic chemist. Cobalt 4 has 5 d electrons. They're in, remember I told you cobalt is in an octahedron? So when you put cobalt in a ligand environment of 6 ligands, you get what's called T2G EG. The electrons sit in the d orbitals. That's what makes inorganic chemists so much special over biochemists and organic chemists. They only have s and p orbitals. We have d orbitals, okay? So there's 5 of them, and then the electrons sit in the T2G orbital. The anti-bonding orbitals, and anti-bonding means repelling. So when you put electrons up in these orbitals, the metal and the ligands repel each other and they fall apart. So in freshman chemistry, if you take freshman chemistry, you do a thing called crystal field stabilization energy, crystal field theory, if you remember that from your first inorganic course, your first chemistry course at Villanova. You get taught that by Jared. So there's 5 electrons at cobalt 4. At cobalt 3, you have 6 electrons. When you get to cobalt 2, there's 7 electrons. It goes high spin and it puts electrons up there. I told you when you populate those orbitals, you repel the ligands. So we knew when we did this experiment, we were going between cobalt 2, 3, 4. We knew we were in trouble because when you get to cobalt 2, and you're going to do that because now these oxygens came from water, I'm going to pull 2 electrons out of there, 2 electrons out of there. That will make the OO bond, and I'll eliminate oxygen. I'm going to drop down into cobalt 2, and the thing's going to fall apart because the ligands are going to get repelled. And that's what happens. Danny Luderman made the cluster out of radioactive cobalt, cobalt 57, super radioactive. Then he put it in just clean water. And radioactivity, you can follow very easily. And so when the thing was working, it was perfectly happy, but when we went to open circuit potential, let it relax, look what happens. We started seeing radioactive cobalt in solution. And that's the cobalt 2. When we put the charge back on the electrode, all the cobalt went back on the electrode because remember, the way we formed it, it was just cobalt 2 in solution, so it repaired itself. This repairs itself. Then it falls apart. Then it falls apart again. What does that allow you to do? We can use this out of any water source. So like on Wednesday, I told you we can use this out of urine. That's good because I can give people clean drinking water because I make O2 and hydrogen. When you recombine it, you get clean drinking water. You can use it off of a puddle. This is a big puddle, the Charles River. It's outside the MIT and Harvard. It's a river. One thing I didn't tell you, you can use it out of seawater too. Right? The guy who did that experiment was this guy, Yogi. Actually, he just took a faculty position at MIT. Let senior faculty remember this, you're so expendable. I left MIT, it took them less than 6 months to go hire one of my best students to replace me. And they said, we don't need you anymore, no sorry, get lost. So they went out and got Yogi, who's a superstar, to replace me. But Yogi You know, when I told them to do seawater, when we did the Charles River water, we went out to the Charles River to get it. I live in Boston. If you're going to do seawater, where would you go? The Boston Harbor. When I walked, I told Yogi after these experiments, Yogi, can we do seawater? He goes, sure, Dan, I'll check that out. And a week later, I walk in my lab, and there's a 55-gallon drum from Aldrich of seawater. I was telling Father Peter, research is really expensive. It's really expensive when students go and buy their seawater instead of getting it out of the ocean. But I just want to tell you, without getting into too many details, and these guys are Quaban is actually from Ghana. Yogi's from the US. But these guys, using electrochemistry, they can turn up the potential, and then they see how fast the reaction runs. And they can see how fast the reaction runs or voltage they need versus pH. By doing those experiments, you make what's called the kinetic rate law. So we know how fast water is split to O2 as a function of pH. And when you take P-Chem, your third term here at Villanova, you're going to get kinetics. And so when you're in that class, using electrochemistry, you can build rate laws. And we built the rate law depending on the number of electrons. That's Nernst's law, 60 millivolts. So Nernst's law is 59 millivolts. You should be learning that quantitative analysis, because I see Amanda shaking her head. So she's taught it to you. Don't forget it. It goes as a function of pH. The really amazing thing is, on the third hole, just like we predicted, it's where you make the OO bond, and by showing that this proton is inversely dependent, it's proton coupled. So it was like textbook that this thing is working this way. What's the mechanism? This guy, Yi Lu, built this instrument. And so what we did is, that's an electrode, so we can do the electrochemistry. So water comes in here. We split water and we make oxygen and hydrogen. The oxygen and hydrogen are in the liquid, which is coming back out of here, but then there's a membrane, so the oxygen and hydrogen come through the permeable membrane, and then we put a mass spec over here, all right? So when you look at these sorts of things, everything I've been showing you, it's voltage versus current, because that's what an electrochemist does. You turn up the voltage, you look at the current. There's voltage versus current. That's called the cyclic voltammogram. But this isn't current. If you look at this y-axis, it's the mass of the oxygen. And it looks like that because now we're detecting in real time, as we scan the current here, what flavor of O2 do we get out of this. So we made a cluster out of O18. Regular oxygen is isotope 16. So we went and bought O18 oxygen, $2,000 per gram, expensive. And then we made the cluster out of it. Then we put it in O16 water. If both oxygens were coming from water to make the O2, that's 16. It should be 16 plus 16, 32. If both oxygens are coming from the cluster, we made the cluster out of O18. 18 plus 18 is 36. Look at this. No O18 oxygen times 2, or no O2 36, but we see O2 34. This is because the label gets washed out. That's not so interesting. But we see that the oxygen's 34. So why would that be? Because one of the waters comes from solution. Remember, the phosphate was there. The phosphate gets pushed out, the water docks. And then one of the oxygens, 18, is from the cluster. So we know that those two are coupling to make the 34O2, 116, 118. That drops down to cobalt 2. And then I just showed you, if cobalt 2 falls out of solution, no big problem. We repair it, and then it reforms, and it keeps on going. And so we figured out now the mechanism for this. And that's the repair mechanism. How about the other side, to make hydrogen? We were using platinum, but now I'm literally out of a glass of water or out of just regular old water. So in less than 3 months, we were able to replace platinum with a nickel molybdenum zinc alloy. I want to say why we did that. but it's just an alloy of 3 cheap metals, nickel, molybdenum, and zinc, and it works like a charm at making hydrogen. Fuel cell people need hydrogen catalysts. Guess what fuel cells do? They operate in concentrated acid again, heavily engineered. If you put this alloy in concentrated acid, it would dissolve in a minute, right? But I'm in a glass of water, so this alloy is perfectly stable. Matter of fact, when we published this, we just put it in a footnote in our paper. We didn't even care, even though it's like one of the world's best hydrogen catalysts in a glass of water. That's what this is telling you. That's the catalyst. I don't want to go into it. So now we can split water using 2 catalysts, right? And I could hook it up to electricity. Our nickel molybdenum zinc catalyst and our oxygen evolving catalyst. And you can go on the web and find out, I told you can get a box using really expensive stuff to make a kilowatt of energy. It's $10,000. Using the catalyst that I just showed you, we can make 1/3 of a kilowatt, but we're only at around $400. So I really have dropped the price out of water splitting. All right, so that sounds good. But you got to keep always driving lower to lower and lower cost. What's the problem with this type of configuration? I have to hook that up to a solar panel, right? And solar panels are expensive. But like I mentioned on Wednesday, and I'm going to mention to you again, they're not expensive because of the single crystal silicon. The single crystal silicon is what absorbs the light, and it makes a wireless current like a leaf, an exciton, electron hole. And what you do at your house is you put the solar panel on your roof, the sun's coming in, an electron comes over here and a hole comes over there. Then you put wires on it and you run it into your house and it powers your electrical systems when the sun is on. When the sun goes down, no more electricity. So what you could do is when the sun is on, run your house, but take some of the current and split water and make hydrogen and oxygen. Then at night, when the sun goes down, you can recombine it and get the energy back. So the problem with this is, though, most of the cost of the solar panel is in the wiring and in what's called the systems engineering. It's not the single crystal silicon. So what we thought was, could we take silicon, now get rid of the entire solar panel, just take the silicon, and now, just like the leaf, we're going to have sunlight come in, we're going to move one electron this way and one hole that way, wireless current and silicon. So now the silicon is acting like the photosynthetic membrane. And then I'm going to I have 2 catalysts where I could put the electrons over here, put 4 of them, put 4 holes in the cobalt catalyst. When I get to 4, I should be able to split water. The one little nuance is O2 plus silicon makes SiO2, sand. So we have to protect the silicon with what's called a transparent conducting oxide. We need an oxide that protects the silicon but conducts electricity. And that's called fluorinated tin oxide. That's what so fluorinated tin oxide can do that. So we thought we could make this, and then that looks a lot like the leaf. I'm not going to show that. But that's like the leaf from a systems engineering. Light in, wireless current, 1, do it 4 times, charge up, not photosystem 1 in the oxygen evolving complex, but our cobalt oxygen evolving complex in the nickel molybdenum zinc alloy. When I get to 4 equivalents, I should be able to split water. So how do you build that? You, physicists in my group, took silicon and then you boron dope it. And then, so that boron has 1 electron less than silicon, so it puts a P plus in there. Then he put phosphorus oxychloride. So remember the periodic table? So right here is silicon, and then on this side is phosphorus, and on that side is boron, right? So this isn't any invention. Electrical engineers already knew this. This is called a heterojunction. Why do you do that? When the light comes in, you make a negative charge and a positive charge. If they're on a flat potential, the electrons and holes are going to run into each other and recombine. So what you have to do is put an internal electric field, like a voltage ramp, So when the light comes into the silicon now, the electrons run down the hill and the holes go the other direction. And that's called a heterojunction. So that's what he made. He made a heterojunction. He put in an internal, biochemically, he put an internal electric field inside the silicon. So all the electrons knew to come to this side and all the holes knew to go to that side of the silicon. And then he did one other quick thing. So what does he do? Silicon, I'm going to tell, now silicon, when you shine light on it, theoretically can put out 0.7 volts. You got to 0.57 volts. Water splitting is 1.2 volts, right? So a single silicon junction doesn't have enough potential to split water. It's like a battery. It's only a 0.6 volt battery. I need a 1.2 volt battery. And it turns out this one was 0.57, but the cool thing is it can run at 26.7 milliamps. When the sun is coming out of the sky on the sunniest day, it's at 30 milliamps. So that means you made a piece of silicon that could make a wireless current and keep up at the rate of the sunlight coming in on the shiniest day. He then needed to put this protecting oxide layer. I told you we use FTO, fluorinated tin oxide. The first time we did this, we used indium tin oxide. We don't like indium because indium's a rare critical material, so we've gotten rid of that. But this doesn't have enough voltage to split water, right? It's only 0.57 volts. I need 1.2. So we had to put little electrode leads on there because we have to wire that up to put more potential to get to 1.2 volts. And then we put it in solution, and now he's running, forget this is silicon, just think it's like Matt Cannon's original experiment where it's just an electrode. And now look at what he did. This looks like what Matt did when I started this talk off. Once he gets up to around 1.1 volt or 1.1 volts, cobalt-2 gets oxidized to cobalt-3, and then in the presence of phosphate, you make the catalyst on the surface of this wafer that's protected with the TCO. And it's on the positive side. This is the positive side of the silicon. This is the negative side. And so here, no light. He's just hooked it up to a battery, effectively. And he gets 1.2 volts, and then he gets this catalyst. But there's one big difference from Matt Cannon's original experiment. This is silicon. So if I then hold it up to sunlight, I told you I'm going to generate a 0.57 volt current. So now, here, this blue curve is with no sunlight, and I told you we needed 1.2, so we're around 1.3 volts, perfect. But now when I turn the sun on, I don't need as high a voltage because I'm using the sunlight to generate the 0.57 volts of current. And you can see for any overpotential, when I turn the sunlight on, I drop by 0.52 volts. This thing can put out 0.57. So we're almost perfectly capturing the full potential of the silicon. So that's why you didn't need to get up to 1.2 volts when the sun was on because this is 0.5 volts less. So now you take 0.5 from 1.3 and you're around 0.7, 0.8. What happens if, now we're going to do a wiring experiment. I want to use wires. That's expensive and I need people to do it. So, but we did this first. We now wire one silicon cell to another silicon cell. Well, when I do that, I'm getting 0.52 volts out of the silicon. Now I have two of them. 0.52 plus 0.52 is 1.04 volts. So now when I have two cells in series, right, so this is more EE than chemistry. When I put two cells in series, I'm going to have 1.04 volts. I need 1.3 volts. So look at what happens. This is now where I'm splitting water. I'm almost perfect at 0.3 volts. This is not rocket science. Now I'm going to add 3. Okay? So if I do that, I shouldn't need any external voltage out of the wall anymore. I can just use the sun to generate my voltage. And then I should have enough potential to split water, but I don't want to wire it, no wires, and I want to be in a glass of water. So this is what the artificial leaf is right now, is we take actually a commercial producer of amorphous silicon, Zunlight, and they make silicon, amorphous silicon. Amorphous silicon absorbs like 400 nanometer light. That's its absorption spectrum. Why is that? Because amorphous silicon, the silicon bonds are tortured, they're bent. That opens the band gap. So amorphous silicon absorbs 400. Then you take a layer of amorphous silicon, you put some germanium in it. The germanium relaxes the silicon lattice. It absorbs more red. Then you put more germanium in. It absorbs more red. Now you take the sum of this plus that, and you get that absorption spectrum. That almost perfectly matches the solar absorption spectrum. So the beauty of the artificial leaf is it's called the buried junction. You can engineer the semiconductor free of engineering the catalyst. So I don't even like amorphous silicon. Let me tell you why. There's no big plant in the world that makes amorphous silicon. So I still want all my friends in applied physics and electrical engineering to make a better semiconductor that can be mass produced. So when they do, we'll just bury it, just the same way here, between our catalysts. Then we put the ITO layer on to protect the silicon. And now when you shine light, look at what you get. Remember before we were 0.52? 0.52 times 3, 1.5 volts. We're basically at 1.5 volts. We have 3 silicons. So before we were at 30 milliamps or 25 milliamps, 26 milliamps. Now I have 3, so take 26 divided by 3, 7, and you get 8 milliamps. This is working out perfectly. This silicon cell is a 7% solar cell. You can get silicon, single crystal silicon, as high as 20%. So keep that in mind. I'm going to tell you why at the end. So I have a 7% silicon cell. So with light in to wireless current at 1.5 volts, this cell operates at 7% efficiency. Then I slap my catalyst on it. So now I'm all set. No wiring. It's just layers of stuff. This is what I said on Wednesday. This is a McDonald's hamburger. Patty, cheese, bun. I told you I was going to be McDonald's. And now what I'm going to show is just the silicon with its coating sitting in water. And on Wednesday, I showed an obnoxious movie, Me. So today I'm going to show a more scientific movie. So here's the silicon, and it's the wafer. And now this is one AM 1.5 solar simulator. So we went out and bought a simulator that puts out sunlight. The sunlight's coming into the front of the silicon, and it's generating the wireless current. 1 unit of charge, a second, a third, a fourth. The holes are coming to the front surface, and the electrons are going to the back because you put in a heterojunction. And that's where the nickel, molybdenum, zinc is on the back, and on the front is the cobalt, oxygen evolving complex. Just under sunlight, no wiring, no nothing, just sitting in an open beaker of water. And so there's the O2 coming off. And remember, the electrons went to the back, so the protons that are left behind are running around to the back, and that's where they're getting combined to make hydrogen, and it's spatially separated, right? And then if you put a balloon on top of it, remember, it's spatially separated. If you put a balloon, what one should be twice as big as the other? Hydrogen, right? Because 2H2O gives you 1 molecule. So you can do that. Put a balloon on there, and the hydrogen balloon is twice as big as the oxygen. Isn't that nice? And there it sits there bubbling all day. Harvard hired me, and all I wanted to do my whole life is do this, and now I've done it. I don't know what to do with myself, so I just sit there and watch it bubble all day. And Harvard's saying, we just hired you. What are you doing? What's next? I said, I don't know. I just want to watch it bubble. So that's what I do now. I like giving this talk because I like watching a bubble. So we can keep driving. I'm about to end. People always ask, what's next? I always hate when scientists say, oh, Nocera said he's done it all. That's what they interpret me saying now. There's nothing else for us left to do. So the first thing I want to tell you is, anytime you have a discovery like this, it's just a door opener. I've never seen one scientific discovery in my life where every scientist has decided problem solved and they go home, right? Organic chemists are still trying to make the same polymer, polyethylene, better and better and better for 70 years, right? So you can kind of start making this better and better and better. So I'm going to only tell you 2 things I'm doing right now to make it better. One is I'm really not like a leaf in one regard. Well, 2 regards. First, I'm not making a sugar because I don't like having hydrogen gas as a fuel. But the other is the silicon is absorbing all the light. But I told you in a leaf you have the light harvesting complex absorbing the light, and then it funnels the light to make the wireless current in the membrane. So you could imagine if I took plastics and stacked them. So now the red light is going to come through here because this only absorbs blue light. This absorbs green, that absorbs yellow, and that absorbs red. So if I stack this plastic, I could use a cheap plastic to do the light absorption. And then, depending on the refractive index, I can waveguide the light. That's why this is glowing around the edges. The light gets waveguided to the edge, and now at the edge, I only put my silicon and artificial leaf. That's going to drive costs down. So we're doing that. That's called photonics. So we're doing photon management up front, because why should I use silicon to do all that light absorption? That's stupid. I might as well use something super cheap to do it. The other thing I'm doing, and Professor Roy Gordon, he's my colleague at Harvard, he's the guy who invented chemical vapor deposition to coat all glass in the world. So all the auto glass, all these windows are all coated. They're all coated by chemical vapor deposition. And what you do is you can have you make an inorganic or organometallic compound, or organic compound. It goes into the gas phase, and then when it hits the hot glass, it decomposes and gives you your compound. So now we're trying to build the catalyst. Roy already figured out how to do TCOs, and we're building new semiconducting materials and look at this glass. You think about doing roll-to-roll manufacturing. You got to do it quickly. Look at what Corning just came out with, flexible willow glass. This is glass, and those guys at Corning and gals figured out how to take glass in a roll-to-roll manufacturing process. It looks like a textile fabric. So now you could imagine with this invention, the glass is going by and we're just spraying, right? Spray, 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 and we can start thinking about making artificial leaves. And the manufacturing rates can go up to 1,000 meters an hour on glass. So we're working on that. To end, I did this as an electrolyzer configuration. You can replace the electrolyzer with an artificial leaf, but it's the concept I want you to think about. So during the day, here's your solar panels. Sunlight hits it. You run the electricity in your house. But at night, the sun's going to go down. So what you could do is bring the current. This is in the electrolyzer configuration, the cheap electrolyzer I told you, or we just do everything up here on a panel. You make your hydrogen and oxygen. You store it in a tank. And then you got to get the energy out. Well, we know scientifically how to take hydrogen and oxygen to make water, and then you make electricity. It's like an inverse solar battery. It's called a fuel cell. So at night, you could run your house based on the fuel cell. What are you going to make after you take H2 and O2? Water again. Then you take the water, you don't release it. Then during the day, you just recollect it, let the sunlight come in, split it. Right? I'm not violating the second law of thermodynamics because there's an input, sunlight. And I'm doing what photosynthesis does, sunlight in, fuel out, and the fuel's hydrogen. We know as a society how to use hydrogen. As I said Wednesday, I would rather take H2 plus CO2 to a liquid fuel because we even do that better. And so you could, your house could be its own power station. And now, why do I say gas station? Because you can take the hydrogen and put it in a fuel cell car. And fuel cell cars already exist. It's the F series for Mercedes-Benz, Toyota, Honda. They all have fuel cell cars, and they're way better than any battery car, right? the reason you don't know about them is you can't go to a gas station and fill it with hydrogen. I will tell you right now, I know both the CEO of Honda and Toyota, guess what their biggest research project is? Instead of this box, they're making a box, you got, you know, methane, natural gas, the price is getting really cheap. They're making what's called a steam reformer to take the methane, instead of taking all the methane to go into your heating system, they're just going to take some methane. Methane, when you decompose it with water, makes hydrogen plus CO2, and then you're making a home refueling station. Because they were thinking in less than 15 years, with all the natural gas coming into your house, if they make a refueling station at night, you'll just drive your car into the garage, hook it up to the hydrogen, to the reformer. You'll have natural gas come into your house, you make the hydrogen, put it in your tank, and drive off for the next day. It's still bad because methane plus water, like I showed on Wednesday, gives out CO2. But it doesn't matter. They're working out that technology, let them keep going, and then I can give them non-carbon-based hydrogen someday. So you see how these different technologies someday can mesh? So if you do that, you don't need centralized energy anymore. We've done this before. You guys don't remember this. There was a thing called mainframes. And then some of your professors used to stand in front of rooms like that with cards, and they would feed the cards into the machines. They won't admit it, because that means they're really old, like me. But there used to be mainframes. And you know who didn't believe in mainframes? IBM. Or they only believed in mainframes. There were these crazy people in the early 80s who said, oh, we'll give computers to everybody. And so what happens, what am I saying? If you never have thought about it, the grid is the computer equivalent, is the equivalent of a computer mainframe. And what I'm saying now is, with discoveries like this, you're going to the personal computing, and that's why I call it personalized energy. This is the only place you can find a mainframe today. That's a garbage dump. There's all the pieces of a mainframe. So now you understand my original picture. I'm out to destroy the grid, which got all the MIT electrical engineers angry. That's why I had to leave, okay? And I'm ending with this picture. So that picture is an interesting one because, by the way, this isn't my house. This is a rich doctor's house in California. I was at a Gordon Research Conference, and National Geographic wanted to take a picture of me, and they said, no, Sarah, we found a rich house, come to it. So it was only like 20 miles up from Ventura. I drove up the coast. And then I asked the guy for his electrical bill, and this is a rich doctor with a big and beautiful house. So he uses 40 kilowatt hours, which is twice the amount of energy an average person uses. And then I said, okay, let me calculate how much water I have to split to do 40 kilowatt hours. And there it is, I'm holding it in my hand, right? Actually, that's very heavy. What you don't see is my postdoc sitting right here, who's also on the faculty now at MIT, Mircea Dinka. And I'm not like some of these guys with their big guns. I can see them out of here, out of their shirts. I have little wimpy arms, and so I would hold it, and it would start, like they would start caving in, and I would go, oh, this is too heavy. And so the photographer had literally around 2 seconds. Like I would hold it, and then all of a sudden I would drop them. And so Mircea's sitting there, and then he would run in and then hold them for me, and then he would put them in and then run away, and the guy would just go click, 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 and then I drop them again. So this took a long time, and this is why I just want to tell you about National Geographic photographers. He wanted to shoot between 5:58 and 6:02. So it was 4 minutes of hell, actually, because he wanted that color of blue in the sky in the background. And he was there for 6 days, and he did all this lighting, and he did one other thing. That's called an F series. That's a Mercedes-Benz fuel cell car that they had Mercedes-Benz drive in. So literally, this is enough water to power that house and get that person around town at around 20 miles in a day. So that's what I'm advocating for the poor. Guess how much that water goes down to? To give 100 watts over 24 hours is 2.4 kilowatt hours, or 1/20th this rich person. Guess how much water? You can do the math now. It's 1/20th of that amount of water. We're drinking Dasani water. Know what Dasani water is, by the way? And you're spending way more than gasoline. Coca-Cola decided, why are we throwing all the water we process Coke down the drain? They put it through 2 ion exchange columns, and they found some smart marketing person. They put it in a bottle and called it Dasani. Go read the label. You're drinking their Coke water, processing water. You only need 1.5 bottles of that, and you can power the world for the poor at 1/20th, this rich doctor. So things are changing. You're not going to have it tomorrow, but the key take-home point is, because of a lot of science innovation, we made a very simple to manufacture, non-highly engineered McDonald's hamburger to give the world energy. So thank you for your attention. I remember Wednesday, the students started off slow, but then it was a cavalcade to this. So go ahead, we'll start. Here's the brave one, and now he's going to open the floodgates for you guys. So now you all can ask me questions. Go ahead.
I'm wondering, so...
What's your name first?
Sorry, Sean Welch.
Hi.
Hi. It's nice to meet you. I'm wondering of the percentage of the photons that are hitting your cell.
Yeah.
When you say that it's creating these gases at the rate that the sunlight's coming in, of the percentage, what percentage of those photons are releasing electrons that have the potential of 1.23 volts to separate water?
Yeah. So that's a really good question, because he's talking about total efficiency, and I forgot to mention this, so here's a smart guy who's paying attention. I told you I was using a solar cell of 7%. That's just to make the electrons. But then you're saying that's got to get translated into making hydrogen and oxygen. So the full sunlight in to make hydrogen and oxygen out, photons in, it's 5%. All right? I'm only using a 7% cell, so that means I'm 70% of the electrons, which is your question, that I'm generating, I'm getting them at 70% efficiency. So that's why it's 5%. And now you're seeing I'm always tied to the efficiency of the solar cell, right? That I would violate the second law of thermodynamics. I can't do better than the thing generating the wireless current. So how do I make this more efficient? There's 2 ways. One is, I don't want to get into the Tafel slope, but the catalyst has a power curve, and we've just increased the power curve and made it steeper. So we can take 5% and get to almost 6.6%, which means I'm almost at 90%. The next thing to do is not use a 7% solar cell. If I use single crystal silicon, I would have to put 3 of them and engineer them a certain way. They can be at 20%, so 20% times 90% would be 18%. The sort of magic number for any fuel system is 10%. The DOE target, by the way, is 6%. So we've already hit the DOE target, but we think we can do a lot better. But that's a key question, because I got to do an energy conversion between the sunlight to the chemistry. But we really have done a good job of that. Overall, we're at 5, but it's because we're not using a highly efficient solar cell. So that's why I said I still want all my friends in applied physics and electrical engineering and material science to keep making me a better single junction solar cell. Other questions? I would have expected he got his degree by now. I'm one of those guys. One of the older students here at Villanova.
Well, yeah.
I'm kidding.
I'm one of those guys who fell asleep yesterday. It seems to me the other nagging energy question in the world has got to do with fixing nitrogen.
Yes.
And I'm wondering if you see any opportunity for the kind of technology you've developed to attack that other,
Yes.
that other issue.
So that's a really great question. So I keep saying well, here's a whole, you've opened a whole can of worms. One is, if I'm fixing H2 with CO2 to make liquid fuel. If I want a hydrogen carrier, I could do what you said. H2 plus N2 to make ammonia, right? And then I could get the hydrogen out of ammonia and get nitrogen back. So first off, this is very connected, and on today, I was supposed to be on a phone call with the DOE that's putting a team together to look at ammonia as hydrogen storage, because you can get a lot of hydrogen on 2 nitrogen molecules. It's a very dense form. And so you could imagine doing H2 plus N2 to ammonia. The other cool thing about that, of course, is then we start talking about food, which is, I think, where you're headed, because that's fertilizer. And so yesterday, when I was talking about multi-electron, multi-proton, N2 plus hydrogen is a 6-electron, 6-proton process. So a lot of the stuff we've discovered to do water splitting in the basic science starts translating to making catalysts to do N2 plus hydrogen to ammonia, which I could use for a hydrogen carrier, or you could think about using as food and fertilizer. Now, we do that on massive industrial scale. Unfortunately, we just saw an accident at one of those plants. But that's done at massive industrial scale. Nobody outside of nitrogenase, in nature we do this, can you do that in a very distributed way. So that demands new science to do N2 plus H2 to ammonia. And if you could do that, you would help solve my hydrogen problem, and you would take care of a food problem for lots of poor people. But the basic science of multi-proton, multi-electron, it's all the same as in water splitting, those basic principles. So I'm not doing it, but I have a young colleague at Harvard who's working hard now on the N2 hydrogen to ammonia problem. And that will become a growing problem in chemistry, I believe, in the next 20 years. I should just tell you one other. You always hear food, water, energy, food, water, energy. This question just started meshing energy and food in a very direct science way, not even in a sociological and political way. How about water? Do you guys realize that how you spend, you drink 700, I got to get these numbers right. I think you use, 4.5 trillion gallons of water. Guess what you use 70% of that water is used for? To cool your energy systems. So I don't know if you go and look at the statistics, almost all water use in America is for energy generation. So when you start doing things like this and you get away from decentralized energy, you're taking a huge step. Forget about the fracking issue. I saw there was a poster here on fracking and the effects of water on fracking. You start making a huge dent in the overall water problem too. So I think you're thinking the right way. When you start looking at this, the food, water, energy triumvirate, they're all at a nexus. And you start helping. It's a beautiful thing because you start solving one, you're going down the road to helping a lot of other problems too.
Hi.
Hi.
I'm Stephanie. We met earlier today. My question is actually about water. And forgive me if you mentioned this in a previous talk, because this was the first talk I could actually attend. It occurs to me, if you're splitting water, and you showed in one of your last pictures about how the water could be stored in a personalized energy situation, and then you could actually re-split it for an energy source. But it occurs to me that you could form water, and that's one of our biggest global crises. And if you can split seawater and urine and things that are not clean sources of water, and then if you recombine it, you're forming clean water. And that to me seems like
just as important.
Almost more, because we can live without energy and just can't live without clean water. And that's, I mean, have you thought about that as and I mean, obviously what you just said is very significant, because one of the uses of clean water is a problem for our energy generation. But to me, it seems like that pops into my mind. yeah, great, this is a fabulous source of, no doubt, a source
Yeah.
of energy, but also to form
Clean
clean
drinking
water
water.
from seawater. That's,
Yeah.
and I know there are tons of people in our engineering department working on that, and I mean, all over the world, really.
Yeah.
But
So you're exactly right. So we aren't pursuing it right now. We put it on the back burner. But on Wednesday, I mentioned there's a company that's formed, Sun Catalytics, and the chairman of the board is Art Goldstein. And Art built the largest water desalination company in the world called Ionics, but it's centralized and he pipes it. And then he sold it to GE. So now if you go on the web, you'll find GE Ionics. But Art's chairman of the board of a company that takes and works on these technologies, and that's not lost on him. And we've been talking about that a lot. So I do think, and it's all because your point is an important one. We can do that because of a basic science discovery of the self-healing catalyst. That's what I don't want people to lose here. If we didn't do that basic science discovery, none of this would be happening, because I couldn't use simple water. I couldn't have simple engineering. You can't use silicon in concentrated base. It decomposes right away. And so you're pointing up another important part. Because of the basic science, that water technology is really important. I will tell you one thing, though. If you have infinite energy, you have basically infinite clean water. Because if I don't have to pay for energy and I can use it, I have lots of ways where they're energy intensive. I can even purify urine, right? And so that's why they're kind of interconnected. It's not one, or they're just kind of meshed in my head together. Yeah.
thank you.
Sure.